Okay, good afternoon. Welcome to this first live talk from the Cognitive Research Group. We have all this series of talks with different researchers on different topics of interest for research in psychology. The Cognitive Group is close to completing 5 years of existence. Initially, it was called the CMAT Group, and later it became to COGNiMATH. The group is mainly made of undergraduate students to whom I send a greeting with great pleasure and to whom I thank infinitely of their effort and work and trust. I am very proud of the work that you have done, and this is thanks to your work and all this kind that we have achieved. So this talk is dedicated to all of you. And it's an honor for me to have Dr. Sudeep Bhatia to start these talks. So we call these days the COGNiMATH days. So let me introduce our guest. If we have any problems of transmission, please let me know. Dr. Bhatia is an assistant professor of psychology at the Department of Psychology in the University of Pennsylvania, and also is the director of the Computational Behavioral Science Lab, also in the University of Pennsylvania. He obtained his PhD in Behavioral Decision Research at the Carnegie Mellon University and his BA in Philosophy and Economics from Tufts University. He has a lot of journal articles, talks, conference, and also had a lot of awards and grants. Who I want to mention one that is very special is the Rising Star Award from the Association of Psychological Science in 2015. And he also has advised so many PhD theses and also postdoctoral positions that he has in his lab. So for me, it's a real pleasure to have him. And let me introduce him and give him his board. The stage is all yours. Sudeep, just let me give you some instruction. I'm going to share my screen for a little bit, so you can have this. You can ask some questions in the YouTube channel over there, but also you can have this opportunity to share all your questions in this presentation that I'm going to put you right in the screen. Let me just start the presentation. You have here, I'm going to show you a link that is going to be for all of you to do some questions over there. I'm going to send, you can see the link over there. I'm going to share with you also on the YouTube. So you have all the free to ask some questions to Dr. Sudeep in this talk. So Sudeep, thank you very much for this great opportunity. So I'm going to stop sharing my screen so you can do your presentation. The stage is all yours.
All right. Well, thank you so much for inviting me. It's my pleasure to give this talk. I think one of the difficulties in this COVID time is that we can't see each other, see other researchers, but there are also unique opportunities like this, so you can now have talks that reach a much broader audience. I'll share my screen now. Let's see. Wonderful. Let me know if you can't see it, but I've got it going. As you heard, I am a psychologist and I study decision making and human behavior. This is a very important topic of research from many disciplines. Research obviously in psychology, but also applied fields like management, economics, the fields of social psychology, policy, health policy, human behavior, understanding how people make decisions is really the focus of a lot of research. So what does this research do? Well, at the core, this research tries to understand how people answer the following questions. So I put some questions on the screen in front of you. And these questions span many different domains. So are electronics cigarettes risky? That's a risk perception or a health judgment question. Is Philadelphia the capital of Pennsylvania? This is a sort of factual knowledge. Is Donald Trump corrupt? That's a political judgment. Will California have an earthquake? That's a risk, again, probability judgment. Is granola healthy? Is Uber a friendly company? These are health judgments, consumer judgments. So as I said, a lot of research has gone into trying to understand how people answer these questions, how they judge risk, or how they judge social perceptions, and how they judge consumers, consumer brands, and so on and so forth. This work has been very influential, but ultimately we don't right now have a mathematical or cognitive model that's able to make predictions regarding people's responses to these kinds of questions. Okay, so here's the thing. When we evaluate everyday objects and events, earthquake, Donald Trump, Uber, we need to rely on stored knowledge representations, things that we know about the world. Now, a lot of research in the behavioral sciences and psychology related fields, they study how people apply this knowledge, like the cognitive process models that might apply to this knowledge, the heuristics that might apply to this knowledge, but not what the knowledge actually is. Okay, so let's go back here. Are electronic cigarettes risky? Well, you know what electronic cigarettes are. Sorry, I just want to confirm that you guys are still following me, right?
Yes, everything is okay. Everything
Wonderful. Yeah, I wasn't. I didn't have any other screen input, so I was worried that I was just talking without. Okay, wonderful.
No, everything goes okay.
All right, perfect. Okay, so you know what electronic cigarettes are, right? And you use this knowledge in order to make a judgment, whether you judge it to be risky or not risky. But the thing is, me, the researcher, I don't know what you know what electronic cigarettes are. So I might have all sorts of sophisticated process models of judgment and decision making and risk perception, but I cannot use these models to make a prediction about your judgments about are electronic cigarettes risky. And the same thing for all these other naturalistic questions, right? I have good models for making binary choices, judgments, yes or no choices, but I don't have the knowledge representations to put into those models to allow them to make predictions regarding these kinds of naturalistic everyday questions. So one way you can think about this problem is like this, right? Right at the top, you have beliefs and preferences. These are things that we care about. We want to understand what people's beliefs are. We want to understand what their preferences are. These beliefs and preferences rely on knowledge representations, what people know about the world. And the knowledge representations themselves actually rely on information environments, the information that they're exposed to, the news that people read, the conversations that they have. A lot of research in the behavioral sciences, this is, again, feels like psychology, feels like management, marketing, economics, social psychology. A lot of these fields have looked at the link between beliefs and preferences and knowledge representations, right? So they've said, oh, people use this kind of process to make judgments or to make decisions. But this research hasn't examined the second arrow. It hasn't really looked at what the knowledge representations are and how you can obtain them from the information environment that people are exposed to. So what I'm going to suggest is that we take these ideas from the behavioral science and we combine them with research in other fields like cognitive science and artificial intelligence, that has ways of extracting knowledge representations from people's information environments. Okay? So what we can do is we can take these ideas in cognitive science and artificial intelligence, apply them to people's information environments, like the news articles that they read. We can use that to extract knowledge representations. Then we can apply theories and models from the behavioral sciences to those knowledge representations and use them to predict people's beliefs and preferences. So you might be asking, at this point, how do you extract knowledge representations from information environments? And that's where this pretty important approach comes in. It's an idea known as vector semantics. It's not just a method for extracting knowledge representations, it's also a theory about what knowledge representations are. The idea underlying vector semantics is very simple. Words and concepts, like electronic cigarettes, they're represented as vectors in a semantic space. So here on the screen, I've showed you a three-dimensional space, and this has words and concepts. It has words like cigarettes and e-cigarettes and electricity and cancer and smoking. These are all points or vectors in a semantic space. Crucially, according to the vector semantic approach, the proximity of these words in the space is a measure of how associated they are with each other. So you can start with electronic cigarettes, and you can see it's very close to vape, which is basically a synonym to electronic cigarettes. But then, cigarettes are also close by, and cigarette is close to lung cancer is close to maybe leukemia. So even though electronic cigarettes are not necessarily close to leukemia, there is essentially a set of associations that go from electronic cigarettes, vape, cigarette, lung cancer, leukemia, all the way there. Okay? And you can understand this in terms of the distances in the semantic space. Now, that's the idea. It's a very common idea in cognitive science. But the power of the vector semantic approach is that you can actually uncover these semantic spaces using large-scale word distribution statistics. Okay, so here I've shown you a 3-dimensional space with maybe 10 or 20 concepts. We now can use spaces with 300 dimensions and millions of concepts. Okay, and I'll be using one such space. It's known as the word-to-vec space or the word-to-vec model. It's trained on a very, very large Google News data set. And it extracts, again, a high-dimensional representation, 300-dimensional representations for 3 million tokens. Okay, for 3 million words, concepts, and phrases. Okay, so the idea here is you're taking people's information environments, like the news articles that they might be exposed to. You're using these technologies to extract representations, which are these semantic spaces. And now these semantic spaces can be used to equip cognitive models with knowledge representations. So it's important to note this approach is very, very, very successful. This idea of using natural language data to extract representations is at the basis of a lot of natural language processing research, a lot of computational linguistics, a lot of machine learning. So as an example, the word-to-vec model that I'm using, this was published in 2013, and it's been cited almost 18,000 times since then. So 18,000 times in 7 years is remarkable. Okay, why do we use these vector semantics? Well, one is they are actually cognitively plausible representations. So a lot of cognitive science uses featural or spatial representations, and these are essentially that kind of representation. And for this reason, they're not only useful for the kinds of applications that I have in mind, but they can also predict a lot of fundamental phenomena in the cognitive sciences. So they can predict, for example, similarity judgments that people have between words. So if I ask human participants, what's the similarity between, let's say, lung cancer and leukemia, people will give a high similarity between those two words, and that can be predicted by the positions of words like lung cancer and leukemia in these semantic spaces. Same reason these approaches can be used to sort of model free association effects, priming effects, and a lot of basic cognitive phenomena. We cover this in a recent review paper of ours in the Current Opinion of Behavioral Sciences. Okay, so that's the idea, right? So you can take people's information environments, like their news articles that they might read. You can use it to extract knowledge representations, which is these high-dimensional semantic spaces with words as vectors. And then you can perhaps apply ideas from the behavioral sciences to these semantic spaces, to these knowledge representations, to predict people's beliefs and preferences. The question here, of course, is what theories, what cognitive models will we apply from the behavioral sciences? The one that I'm going to start with is association. It's a very, very simple idea that's used in a lot of research in judgment and decision-making and in the study of beliefs and preferences. What it says at its core is that people, when they're making judgments, they use the strength of association between the words that they're given as a heuristic cue. So items that are associated with a judgment prompt end up being activated due to these associations, and then people are more likely to use them as responses. Why is this a good heuristic? Well, the association is a very basic memory process, and it's oftentimes adaptive as well. Your memory, your association oftentimes reflects the environment, so you can use association as a simple heuristic when making judgments. For those of you who have heard of Daniel Kahneman and Thinking Fast and Slow, he's popularized the idea a lot. It's a very well-known book. He won the Nobel Prize also. This heuristic, the association heuristic, is the fast part of his theory. Okay, let me give you an example of how we can use this idea. So I'll give you a question, all right? And maybe you can think about what the answer is. So I'm going to describe you X. X has black fur and orange eyes, and she likes to sit inside empty boxes, and she stares at me while I work. Okay, what is X? And maybe you're thinking, is it a car? Is it a cat? Is it a cow? I'm going to guess that many are going to say cat. It is, in fact, a cat. That's my cat. And so that's the right answer. How did you get this answer correctly? Well, you saw words like fur and sitting inside empty boxes and so on and so forth, and that seems to describe a cat more than it describes a car or a cow. All right. Our model can now answer these kinds of questions as well, the way humans answer these questions, right? So think about the question. The question is a set of words like black, fur, orange, eyes, so on and so forth. And each of the responses are also words. What we can do now with these vector semantic models and with these theories of association is measure the association between each of the question and each of the responses. All right, and we do this by first obtaining a vector representation for the word. This is finding where the 300-dimensional space the word is. We average the words in the question and in the responses to get one single aggregate vector representation. Then we measure the distance between each of the question vector and each of the response vectors. And this allows us to calculate a measure of association. And then we predict that the decision maker will choose the response with the strongest association. Okay, when we apply this algorithm to this question, our model predicts that that cat has the strongest association and that you will choose cat, and the model is right about that. Okay, so this is a very, very powerful idea, right? So now we can take any question, any natural language judgment question that we might want to offer our participants, and we can give the same question to our model, and our model can make a prediction about the associations involved. And that's a pretty powerful idea. We're going to test that. And I tested it with a number of data sets. I'll show you one of these data sets. This is a data set of questions. These are multiple choice questions with 4 response options. The first data set in this is a set of geography quiz questions, about 1,000 questions. I also have science and social science exams. There are about 440 questions. And also Who Wants to Be a Millionaire question. So Who Wants to Be a Millionaire was a very well-known game show here in the United States and also in many other countries, and you may have heard of it. We got around 2,700 questions that were actually used on that game show in the 2007-2008 season. And what we did was we gave these questions to human participants, and we asked them to respond to these questions. And our goal was to predict what they will respond. So what did we do? What did we find? So this, for example, is an example of Who Wants to Be a Millionaire question. So this is someone on the game show. Homeowners buy surge protection to protect their possessions from unexpected surges of what? That is the question. The right answer is electric current, but this participant incorrectly said water flow. Now we want to make sure that our model is able to predict the participant response, because we're psychologists, we care about what people will do. So we want our model to predict water flow, even if that's the wrong answer. Okay, how does the model do? So here I've shown essentially the model's accuracy rates, and importantly, it's the accuracy rate at predicting the participant response. Not its accuracy rate at getting the question right, but rather how well it predicted the response that was actually chosen by the participant in our study. So the green bars are how often the model's first guess, the response that it thinks is the most associated with the question, how often that response is the response that the participant chose. The yellow bar is a second guess, the orange bar is a third guess, and the red bar is a fourth guess. And you can see there's a very, very clean link that the model is able to predict quite accurately the response chosen by the participants. In other words, the model's first guess is in fact the participant's guess as well. And we find this running a number of statistical tests that control for a lot of variables, like whether or not the response is correct. We also allow for participant random effects and so on and so forth. So we find that we're able to actually predict participant responses to real-world judgment problems. On average, we get an R-square of 0.44, which is quite nice in my opinion. Let me give you another example of how we can use this work. This is a probability judgment question. It's a very well-known question in the judgment and decision-making literature. And the question is as follows. So Linda is a 31-year-old, single, outspoken, and very bright person. She majored in philosophy. As a student, she was concerned with issues of discrimination and social justice, and also participated in anti-nuclear demonstrations. What is she more likely to be? Is she more likely to be a bank teller or a feminist bank teller? Okay, I'll let you think about it for a few seconds. Is she more likely to be a bank teller or a feminist bank teller? Well, most people, when given this question, they say feminist bank teller. Now, this is the wrong answer, because realize that every feminist bank teller is also a bank teller, so it's just logically impossible for her to be more likely to be a feminist bank teller than a bank teller. Now, we want our model to predict this fallacy. We want our model to predict response 2, which is the standard response that people give to this kind of question. And in fact, our model does predict that. Our model has an association of 0.35 with response 2 and an association of 0.26 with response 1. So our model will also, like human participants, predict that that Linda is a feminist bank teller. Okay. Now, this, as I said, this approach is very powerful. So now we can go back and look at all the papers in psychology that have tried to study these kinds of conjunction fallacy problems. It's called a conjunction fallacy because the probability of Linda being a feminist bank teller, it's essentially a conjunction of two events, feminist and bank teller. So that probability must necessarily be less than the probability of her being a bank teller, but people don't do that. Okay, so we can go back into psychology literature and find all the problems that were used by researchers to study this kind of fallacy. We got variants of this Linda problem that I just showed you from Kahneman and Tversky's work. We've got problems from other papers that have tried to argue for different theories of why people are making the conjunction fallacy. We can also get other types of fallacy problems. So disjunction fallacy, it's a very closely related fallacy. Base rate neglect is another kind of statistical fallacy that people use. And we can even ask our participants to generate these problems, okay? So in all cases, we're able to describe the finding that people may have a conjunction fallacy, and we were able to accurately describe the conjunction fallacy rates across these data sets. On average, we get an R-square of 0.29 across these data sets. So that's, again, showing that we can go back and start modeling existing judgment research. Now, we've used this research quite a lot in a number of different applications. So, for example, we can start predicting how people forecast the future. So what's the probability that there'll be an earthquake in Japan or in California? We can start predicting that by measuring the association between, say, California and earthquake. We can also do what are known as city size judgment problems. This is another type of problem that's very, very well known in the judgment literature. We can also model responses to actual real-world problems in real-world game shows. So Jeopardy is a very well-known game show. A couple of years ago, IBM released the Watson algorithm, or the Watson sort of Jeopardy player. It's a computer that can essentially play Jeopardy, which is the quiz show. Our goal is not to play the quiz show. Our goal is to predict the responses of the people who play the quiz show. So we're able to do that pretty well. And in other work, we've kind of taken this idea that we can model associations using proximity in a vector semantic space to study things like social associations, like prejudice and stereotypes. We can study decisions from memory. We can study political judgment, brand perceptions, gender associations. A lot of these very, very important topics in psychology that rely on the idea of association. But what we can do now is actually quantify that association using these semantic models. I'll give you an example of how you can use this, for example, to study brands. So here are two brands, Apple and Microsoft. You may remember a couple of years ago, there were these advertisement campaigns. You know, Apple was like, oh, I'm so cool. Microsoft is not cool. Anyway, so the point is, like, you know, can our model also pick up these associations? Well, here I've taken Apple and Microsoft and I've given the model a bunch of words like charming and imaginative and honest and genuine, efficient and tough. And I've seen how associated Microsoft and Apple are with these words in the Google News corpus using the vector semantic model that's trained on the Google News corpus. And you can see that, for example, this model essentially picks up the stereotype of Apple as being charming and imaginative and creative, and Microsoft as being a little bit more honest and genuine and efficient. So the model can start predicting brand perceptions, which is another valuable application. Here's another application of this model. This is to trait associations with Donald Trump and Hillary Clinton. Remember, the model was trained many years ago. It was trained in 2013, so this is before the US presidential election of 2016. And so these are the associations that the model had with Trump and Clinton before even the election happened. And you can see that there is a lot of interesting things going on. So Hillary Clinton, she's the model judges her to be seductive and motherly, but also tense and violent. Trump is greedy, he's conceited, he's strict, he's cocky. These are the kinds of associations that people may have had leading up to the 2016 election. So you can use this approach to study that. And we've actually done that in some of our research since then. Okay, so I don't know how I'm doing on time. I don't know if there was a question. Let me just make sure that we're doing all right.
Yeah, we're doing very fine. If you want to continue, we have some questions, but you can continue, and then maybe at the end we can ask the questions.
Wonderful. So let me go for another maybe 10 minutes or so, and then we can.
Yeah, for sure, for sure.
Okay, wonderful. So this is the outline that I'd presented to you earlier, right? So we've got beliefs and preferences. That's what we want to study. We want to model people's beliefs and preferences, their beliefs about electronic cigarettes, or Linda, the bank teller, or Trump, or whatever. We want to be able to predict that. We do that by measuring association on knowledge representations, and we get the knowledge representations using vector semantic models that are trained on people's information environments. We take Google News articles, we train a model that builds a vector semantic space based on word co-occurrence statistics on that corpus, and then we measure association on that, and we use that to start predicting people's beliefs and preferences. Now, you may say that we don't care about association. Maybe we only care about prediction. So can we maybe take this idea and not actually worry about having a cognitive or memory-based interpretation at the top? Maybe we can just use let's say like a simple machine learning approach to start predicting people's beliefs and preferences. So let's look at that possibility. Here's the general idea. Okay, so let's say you've got our vector semantic space here, and you're asking people to make risk perception judgments. So how risky is electronic cigarettes? What you can do is learn using basic like linear regression techniques, ridge regression techniques. You can learn a mapping from this high dimensional vector space onto participant responses. So if your participant says that electronic cigarettes are very risky, that's in some sense an observation. And you can essentially then take this sort of linear model that you've trained on some participant data to see if it can predict out of sample people's judgments, say regarding the riskiness of other items. So that's what we did, and I want to show you a nice illustration of this possibility. We asked participants to rate the riskiness of different types of risks. So we had 125 technological risks, 125 activity-based risks, and then we even had 200 participant-generated risks. These are risks that were generated by our participants. And what we asked our participants to do was to rate the riskiness of each of these risk sources. So for example, they might see cell phones, and they can rate it as being risky or not risky on a scale of -100 to 100. Our goal was to build a predictive model so that to try and predict out of sample risk perception judgments. So if our training data essentially has cell phones, heroin, X-rays, and we have people's risk ratings, can we learn a regression model, for example, that takes the semantic vector representation for these risk sources, learns a mapping onto the risk ratings, and then we can go to an out-of-sample risk source, say painkillers or electronic cigarettes, apply the trained model on the semantic vector representations for those risk items, and make predictions regarding people's risk ratings. So we'll do an out-of-sample prediction. That's the goal of trying to do this. Now we wanted to compare our method with existing approaches in psychology, and for that we used the best known approach in the study of risk perception is known as a psychometric approach. Here's really what it asks people to do. It asks people to take these risk sources and rate them on a number of psychometric dimensions. Dimensions like whether or not the risk source involves voluntary risks or immediate risks, and so on and so forth. So you get participant ratings on these risk sources, and you can use these ratings to then predict people's risk perceptions. It's the way psychologists study risk perception currently. This approach needs 10 times as much participant data in order to make risk perception judgments. So it's not as it needs just far more data. Okay, but you can do the same thing with it. You can, instead of taking the 300-dimensional semantic vector representation, you can take the 9-dimensional vector of responses. These are 9 questions here, and do the 9-dimensional vector of responses to those questions, and build a regression model and use that to predict out-of-sample risk perception judgments. So how does our approach do relative to the standard approach? We find that in most of our studies, which involve technological risk, activity risk, participant risk, the two approaches do fairly comparable. They do roughly equally, despite the fact that the semantic vector approach requires very, very little data. It just uses Google News to get people's, in some sense, perceptions for the risk source, and it's able to do predictions through that instead of asking them for their psychometric survey ratings. When you combine the psychometric and the semantic vector approach, you can get much higher accuracy rates, showing that the combination of the two approaches is actually very, very powerful as well. So there's it shows that you can maybe combine these semantic vector representation models with existing methods in psychology and do really well like that. Remember, I told you that this was almost like a predictive approach. There was no psychological theory underlying it. All you're doing is doing a regression where you're regressing the variable that you're trying to predict, which is risk perception, on the vector representations for the words, for the risk sources. When I said that, I was actually lying, because there is a psychological interpretation. In fact, you can interpret this in terms of association itself. If you're using a linear model, which is what we've done, a linear mapping, then implicitly what you're doing by learning that linear mapping is identifying a point in the semantic space that's most associated with judgment. It's implicitly associated with judgment. So in some sense, when you're building this regression model, you're sort of finding a latent representation for risk, that associations with that risk representation predict people's responses. Okay, what are these representations? Well, the words and concepts that are closest to this latent representation of risk, for the technology risks, drugs, substance, danger, disorders. For activity risks, you get words like helmet, dangerous, fatal, combat. For participant-generated risks, you get words like tragedy, violence, deadly. In essence, what this approach is doing is, in a bottom-up manner, revealing the structure of associations that is generating these risk perception judgments. Okay? Ultimately, the risk associations that this approach finds are actually higher in emotions like fear relative to other emotions. So you can even do psychological hypothesis tests on this in order to test psychological hypotheses. For example, the role of fear in risk perception. Okay, so we've taken this approach further. In a recent paper of ours published this year, we show that we can use the same approach to predict judgments across many, many different subfields of psychology. Okay, we collected a massive data set of participant judgments, 140,000 participant judgments on over 1,400 natural entities and 14 dimensions. And on average, we're able to obtain an R-square of about 0.58. Okay, so it shows that you can use the general idea to predict all sorts of judgments, not just risk perception, but social judgment, health judgment, occupational judgment, many, many domains that psychologists are interested in. And we're taking this approach further. We've got a number of projects that are currently in progress, where we're applying it to different domains like consumer judgment, again, leadership perception, health judgment. It's a very, very powerful approach. So that's essentially, I think, all we have time for. I did have a couple of other projects I could talk about, but I think we're out of time, so I won't do that. Just to summarize, when we try and model human behavior, we're often trying to model their people's beliefs and preferences. They're essentially their judgments and decisions about entities in the world. With this approach, we can do this. We can build cognitive computational models that are able to make predictions about beliefs and preferences for natural entities in an out-sample manner. We do this by combining existing theories in psychology regarding association with knowledge representations that are derived from theories in cognitive science and artificial intelligence. These knowledge representations are obtained from people's information environments. So this allows us to essentially know what people know, and then build a process model that uses that knowledge the way they use their knowledge. And so with that, we can essentially mimic their beliefs and preferences. I think it's a very encouraging approach, and I'm very happy to have been able to share this with you guys. Let me move forward to the final slide. I did have some stuff on the drift diffusion model here, but we don't have time to do that. unfortunately. Thank you. These are members of my lab who have helped out with this research. Wenjia Zhao, Ada Aka, Wang Lingzu, Desheng He, and Russell Ritchie. So thank you for listening.
Thank you very much. Thank you very much, Sudeep. Thank you very much. It was a very interesting topic that you presented us. We have a couple of questions. If you want to answer this one, let just me here. Manuel is asking, for the correlations you mentioned in your graphs, are there results based on other variables like gender, age, for example?
Yeah, so good question. So the correlations that I showed did not explicitly study individual differences, but we have used this approach to study individual differences in other domains. So for example, can you model the differences between experts and so we've got another project where we give expert nutritionists food items to make health judgments for. So how healthy is a different food item? And we also give lay decision makers, so normal people, those food items. So our goal is to predict the difference in the health judgment between the expert and the lay decision maker. And we can do essentially what you're suggesting. So we can study these correlations as a function of the subgroup, and we can start predicting differences between the groups. And this is another powerful way of studying individual differences in judgment.
Okay, thank you very much. I have another question here from Pablo. You think it's possible to extend your model to predict where a human can fail in a process, for example, administrative red tape and assembly line process?
Yeah, good question. So I showed a slide right at the very start. You may remember there was a screenshot from Who Wants to Be a Millionaire, in which the decision maker, or the participant in that game show, that person incorrectly chose the wrong response. It chose a water rather than electricity or whatever the question. So yeah, so if the model is able to mimic human behavior, then it can predict where humans will fail. Now the problem is, I don't know whether you can start using this to study administrative issues like administrative red tape, because then that's a more complex domain, but you can definitely use it, for example, to study failures in simpler settings. So, when you look at stereotypes, a lot of harmful stereotypes are failures of judgment, because you're making a biased and incorrect judgment based on information, based on associations that you have, associations that are maybe that you get from reading the news, or maybe you get from these information environments. Well, if we can predict those associations, we can predict your failures, we can predict your biases, your stereotypes, your prejudices, and that is important for many, many applications.
Excellent, thank you very much. We have another question right here from Salim. Particular attributes like risk seem to be the co-vectors in the semantic vector space, since one can make it a linear map. How self-inconsistent in this? For instance, how similar is the vector for risk to the linear mark for risk, to the linear map for risk?
That's a really good question. I think that's a brilliant question. So here's the thing: they are similar, but if they were identical, then the simple association approach would just look at the association with the word risk, would be able to do as well as the sort of, let's say, machine learning approach, because they'll be relying on the same representation. But the machine learning approach does better, or the mapping approach does better, showing that that in most cases the vectors are slightly different, and that identifying the better vector using the mapping or machine learning approach can improve predictions. That said, I haven't looked into too much detail about the differences between the original word vector and the vector that's uncovered from the mapping. I think understanding those differences would be very insightful, because the word vector, the risk vector that you get in the untrained model, reflects how the word risk is used in natural language. Whereas the one that you obtain by training the model on participant judgments, that reflects people's latent representation of what a risky thing is. Those are sometimes same, sometimes they're different. And understanding those differences is very, very interesting in my opinion. That's a really good question. Thank you.
Okay, thank you very much. We have another questions that they sent before the talk. They're more like general kind of questions. So let me ask you some of them. They ask if, let me just take it right here, like, sorry, I missed the one that I was looking for. But they are asking about the reliable that you can have on these kind of cognitive models.
The reliability?
Yes. About... Yes, just let me... Sorry, I missed the question. I have a question here. Sorry. I can ask you another one here in the meantime. Look for the other one. The proposed model that you can that you show, they can be applied for moral, social decision making.
That's right. That's right. So they can. So I didn't give you too many examples of social decision making. So they can be used for social decision making. Like, we have a paper on perceptions for Trump and Clinton. So by studying news articles, we can extract the associations that people have for Trump and Clinton in the 2016 election. So I didn't get into that in too much detail, but we can do some interesting work there. Moral judgment as well, right? So we haven't, again, actively studied moral judgment in this area, but you can sort of, for example, try to model whether or not certain acts are judged as being harmful or not harmful, again, based on the way those acts are discussed in natural language, the associations that those acts have, and the representations that measure those associations that are obtained from like news articles and other resources like that.
Okay, thank you very much. And this general question: are these computational models meant to be used merely as a tool for better understanding the human cognition, or there is any other use of them, such as the creation of programs that can substitute psychological therapy?
Interesting. Yeah, I haven't thought about psychological therapy much. I think that is an interesting avenue for research. So it's clear that there are many practical applications. So, if you're like a company and you want to understand how your brand is perceived, you can use these tools to measure the association that consumers have with your brand. Or let's say you're a policy decision maker. You want to understand how people perceive electronic cigarettes, how they perceive coronavirus, how they perceive other risk sources. You can kind of use this approach to study that. Now, let's say you're a clinician and you want to understand how to, maybe there's, people with anxiety have different perceptions. I suppose you could try and apply it in that setting. I haven't thought too much about it, but I would be optimistic about such an application.
Okay, thank you very much. We have another question from Alejandra. Why is R square value small for this type of model compared to such areas as chemistry or physics?
Yeah, well, welcome to psychology. So in psychology, R square, like a 0.4, is seen as a big effect. If you're going to explain 40% of the variance, if you can do an R square of 0.4, you're doing really, really well. And we're getting around 0.4, 0.5, 0.6 in out-of-sample predictions, which for psychology is amazing. And obviously in physics, that's really, really, if I predicted, the turbulence on an airplane with a R square of 0.4, we wouldn't be taking any flights, so obviously there's difference. So here's the difference. Human cognition is very, very noisy. At any given moment, many, many things can influence my judgments. What I ate, what I saw yesterday on the TV, how I'm feeling, if I'm angry or sad. All of those can influence, if you will, the parameters that guide my judgments and decisions. In contrast, the parameters that describe our physical universe are more or less constant. I mean, gravity is gravity, 9.8 meters per second squared. So there isn't that much, let's say, time-to-time variability in many physics processes, such as the ones that are typically associated with very high R squares. I can imagine there are domains of physics. I'm not a physicist, so I can't comment on that. I can imagine there's domains of physics that are susceptible to a lot of noise and that have lower R squares. I can't comment on that, but that's my impression about the different. Psychology is much harder to study than physics for many reasons. Technically, I feel our research, our methods are far simpler than those in physics, but the observations are far messier. So.
Thank you very much. And I have two questions that are more related to the training that you must have for this kind of models research. So they are asking, what is the educational material, the knowledge, the background that they must have in order to start to doing this kind of research of the model that you propose? And I want to take another question in this sense. How can they apply for doing some research stay or some graduate studies or postdoctoral studies with you?
Okay, well, yeah, those are both very good questions. So I think these methods are actually pretty easy to work with. So there's two sets of methods, actually. One is kind of computational modeling of decision processes. So some of you may be familiar with like the applications of a diffusion model to decision making. Those require a little bit more of a statistical and mathematical ability. So if you like thinking about dynamic systems, dynamic stochastic systems, take a class in statistics, take a class in probability. You'll get a feel for how those things work, and then you can start applying those models to human cognition. The other set of models that I use are these sort of vector semantic models. There's not so much statistics, but it's basically like machine learning or natural language processing. That's a different set of skills. That's kind of more. I don't think it requires like detailed like sort of mathematical knowledge. I think it requires a little bit more, say, programming expertise. So like, how do you scrape a data set? How do you build a algorithm that can sort of do this without wasting too many computational resources? That's a little bit more programming. So if you find that sort of stuff interesting, again, take a computer programming class. Take for both statistics and probability as well as for like programming, you can take online classes like Coursera. Those are very, very useful. So I would recommend that. So that's sort of the skills or the background that you need to get involved. Now, how do you actually get involved if you have that background? So I would recommend looking for summer undergraduate. So I guess most of you are undergraduates. Is that correct?
Correct.
So look for some. Here, let me actually send you a link to one of these. Let me just find the link, and I'll send it on the chat, and or maybe I'll share it with you. Sorry, give me 1 second.
You can send me on the chat, and I can put it on the YouTube.
Yeah, I wanna, so
a message.
Yeah. So
there's a bubble in the left corner.
Yeah. Give me 1 second. There are a couple of different summer programs. Here, well, actually, you know what? I'll just tell you to Google MindCore, MINDCORE. I can share the screen so you can go to the web page. This is a sort of center at the University of Pennsylvania that studies cognition. And then if you look at their education section, they have a number of opportunities for undergraduate education. They've got summer fellowships. Some of these are for UPenn students, but many of these are also for non-UPenn students. So UPenn has those. UPenn has those, and so do other universities. So find those summer programs where you can go get involved with faculty, and then you can use that as a way to sort of make connections with research faculty that you can then end up doing a PhD with. So you'll have to do a little bit of research, but many universities have these summer programs in psychology, in cognitive science, in different fields like that, and you can sort of track those down.
Okay, thank you very much.
Yeah.
We have another question here. Will you say your model will be able to predict the outcome for social events? For instance, what recently happened with George Floyd?
I don't think so. I think the model, yeah, okay, so here's the thing. If you were able to know what people know, like you can say, oh, I think this person thinks this and this other person thinks this and that person thinks that, would you be able to predict the future? I'm guessing maybe with an R square of 0.005 or something like that, with a very small R squared. If that's the case, then maybe you can use these techniques because these techniques allow you a window into people's mental representations. On the other hand, I'll be honest, I don't think you could predict things like, these sort of social events, such a chaotic system that it's very
yeah.
But you could, one thing you could use this to do is study things like, where can you do interventions to help with this kind of approach? So people are using this approach to study things like racism. You can identify places in America that suffer from racism using, say, Twitter data. By training these models on Twitter data, you can uncover the associations, racist associations, and build interventions like that. So I think there is a way to use these for social and public purposes. I don't think prediction of the future is one of them.
Yeah. And they are asking me for if you can, then later you can recommend some book or paper that they can follow for this kind of topics.
Well, let me just here. Let me just show you one. So here I'll share my screen. If you right now go on, just Google. I googled understanding Word2Vec. Word2Vec is that model that I've been using. There are so many blog posts showing how it works. You know, how is it trained? How does it work? How do you get started using these models? It's very, very easy to do it. Because this is such an important technology right now, you can just go and read these blog posts. These blog posts are written for normal people without too much background. They give some Python code. You know, you can just Google it and you'll find so much useful information. I don't think you need books. I don't think you need to spend any money on books. Just Google how does Word2Vec work, and then read that, and I think you'll learn as much as you need to know.
Excellent, excellent. Thank you very much. And I have a final question in order to close this very nice session. And I thank you very much again, Sudeep, for this very, very interesting topic and your disposition for this invitation that the Cognitive Root has made to you. So my final question is, you are working in another kind of mapping that you can do not only for this linear kind of stuff, another kind of mapping that you have in mind. I don't know, maybe a multi-dimensional kind of stuff that you have, not only this two-dimensional space, or maybe a more dimensional kind of scenario?
Yeah, good question. So, you know, the latest version of these models, I'll tell you what the latest version. So Word2Vec, the one that I was using, is from 2013. So that's 7 years old. That's a long, in computer science these days, that's a very long time. So the latest model that's that maybe you can Google. Again, you should Google this. Google BERT. So the name of the model is Google BERT, B-E-R-T. That is the latest version, or that's the newest approach to studying this approach. So that's essentially a deep network that can take in sentences, and if you give it some output to sort of train with, so maybe it could be a single-dimensional output, or it could be a multi-dimensional output, it could be another sentence itself, like it could be sentence-to-sentence prediction, it could be translation, whatever. The model is able to learn. It's very, very powerful approach, very easy to use. It is responsible for all the breakthroughs right now in natural language processing. So we're using that in many tasks that involve more complex mappings about sentences and words, tasks for which we have more data to train a deep network. So sometimes we don't have that much data for deep network in psychology. So if you do, then you can use these more complex approaches. And we've got some very promising results. So we're very excited about it. So maybe next year I can tell you more about that.
Thank you very much. Once again, Sudeep, thank you very much for this opportunity. I hope you have a good time with us here in this talk. And thank you very much. And I hope that we can see you here in Puebla in the near future. So thank you very much, Sudeep. And I don't know if you want to send a final message for the people that are watching us. We have at one time we have 80 people connected. So if you have a final message for them.
No, well, thank you so much for attending. I hope you find it interesting. If you like this work, shoot me an email. You know, I think this is a very good understanding these computational models is a good place to invest your energies in. So thank you for giving me the opportunity to share my research.
And thank you very much, Steve. And thank you very much to all of you. And we are closing now the YouTube transmission. Stay tuned for all the next activity that we have in the next weeks. Thank you very much.